Hi, my name is Dan Gwynn. I'm currently a World Campus student working on my master's in mechanical engineering, and my final presentation is on high performance polymers and composites in fused filament fabrication. We're going to go over a quick overview of high performance materials, and we're going to talk to three forerunners in this field, specifically Ultem 9085 PEEK and the nylon 12 carbon fiber. We'll compare the three to both aluminum and titanium alloys and then have our conclusion. New improvements in material science, specifically polymer science, have recently permitted the manufacture of end-use products in demanding applications. Some of the fields for these products include Formula One, aerospace, space, and military applications. On the left side is a part manufactured by the McLaren Formula One team via FDM from Stratasys ABS Plus material. The middle section shows a wing section created from PEEK, and at right is a printed manifold for use on a naval V-22 Osprey. In order to meet the strength and temperature demands of these applications, specialized high modulus materials were required. Some of these requirements have been filled by additively manufactured metals. However, there are numerous applications where polymers would be desired. Some reasons for this may include cost, weight savings, corrosion resistance, or the need for a non-magnetic or non-reactive material or a flexible material. Ultem 9085 is a high-performance polymer created by Stratasys. 9085 is a thermoplastic polyether imide mixed with polycarbonate copolymer for an improved flow, and its chemical structure is shown top right. This particular material is advertised by Stratasys as being a flame-retardant, high-performance thermoplastic for both manufacturing and rapid prototyping, and has a good flame, smoke, and toxicity rating. By meeting the aircraft flammability requirements of FAR 25.853, Ultem 9085 is unique in that it is certified for use in aircraft today. Certified Ultem 9085 comes in a tan or natural color as shown at bottom right. High performance applications of Ultem 9085 to date include an environmental control system or ECS duct used by United Launch Alliance on a space launch vehicle. Again, see the picture at bottom right. This reduced the system's production cost by 57%, and the part count of the ECS assembly was reduced to 16 parts from over 140. Another example not shown is Indero, a Spanish aerospace company, which used Ultem 9085 to build custom fit tools for an Airbus helicopter. Here's some mechanical properties. Of note, tensile strength at yield and ultimate of the resin material report at 47 and 69 MPa respectively. Heat deflection temperature is 153 degrees C and glass transition temperature is 186 degrees. PEI is amorphous and therefore has no melting temperature. Ultem 9085 is readily available for purchase and current as of this writing could be found for $125 for half a kilogram of 1.75 millimeter filament for FDM. Polyether ether ketone, or PEEK, is a semi-crystalline high-performance thermoplastic. Its molecular structure consists of aromatic groups and a backbone of ether and ketone groups. This gives the polymer excellent thermal properties, a glass transition between 143 and 148 degrees C, melting temperature between 330 and 340 degrees C, and surface temperatures up to 260 degrees C. PEEK also exhibits good chemical properties. It's only soluble in sulfuric acid at 60 degrees C and has extremely high mechanical moduli, especially for a polymer. Its tensile strength is around 100 MPa and its modulus of elasticity is 3.5 gigapascals. Its chemical structure is shown at top right. Some examples of PEEK usage are as follows. So bottom left picture shows a mixer created by FDM from PEEK. The bottom middle picture is an impeller system also manufactured from PEEK by FDM. And at bottom right is a bracket fitting used on an Airbus helicopter door. Stratasys has also begun marketing a polyether ketone or PEKK FDM filament, a close cousin of PEEK, another thermoplastic in the polyether ketone or PAEK family under the name Antero 800NA. While PEEK materials have impressive moduli for polymers, they are also very expensive. In this case, for half a kilogram of 1.75 millimeter filament, expect to pay $325. In addition to excellent mechanical properties, PEEK is also FDA approved for use in food contact. One of the difficulties in additive manufacturing of Ultem 9085 and PEEK is that they have high thermal properties, which is also its advantage. But as such, they need to be extruded at high temperatures to be above 350 to 400 degrees C. This brings us to another commonly used material with high strength properties, but lower thermal requirements and also capabilities. Polyamide, or PA, while a common material in additive manufacturing including PA6, 6-6, and 12, or nylon, has limited uses in demanding applications due to limited structural and thermal properties in and of itself. Great strides have been made in recent years in the field of composite additive manufacturing. One such material is a composite PA12 and carbon fiber mixture. The addition of only 10% weight carbon fiber to neat PA12 filament increases its tensile strength and flexural strength by over 100 and 250% respectively. Depicted at the top is the chemical structure of nylon 12. Stratasys advertises its FDM nylon 12CF with 35% carbon fiber as the highest stiffness to weight ratio composite of any FDM material. Nylon 12 polymers, while lacking in strength by themselves, are excellent material choices for high fatigue applications. Combining these properties with carbon fiber makes a useful composite material for a wide array of applications. At the picture bottom left, a bike frame is being assembled using Stratasys nylon 12 carbon fiber as joining brackets. At bottom right, the McLaren Formula One racing team used a nylon 12 carbon fiber to FDM manufacture structural bracket for a hydraulic line. Carbon fiber reinforced nylon 12 is much more affordable and can be purchased for $68 for 0.75 kilograms or equivalently $45 for a half a kilogram of 1.75 millimeter filament. While nylon exhibits excellent fatigue characteristics, it struggles with high moisture absorption rates. To compare all three, look at the following table. In this particular comparison, note that polymer properties are for printed FDM material. Metal properties are from stock material, not metal AM results. A price comparison was not included between the metals as well as the plastics, as metal AM with the tabulated materials would likely be performed with either an SLS or an electron beam melting machine using a different form of feedstock. A cost analysis would need to be accomplished in order to fairly compare the costs between these two. All three of these advanced materials provide significant advantages over traditional AM materials, including ABS, PLA, and basic nylon. Ultem 985, PEEK, and Nylon 12CF are providing materials today that can be additively manufactured as high modulus and use parts. These materials provide niche solutions to engineering problems in the examples detailed throughout our presentation. PEEK was the highest moduli polymer examined in this paper. With excellent tensile strength and heat properties, it would make a great choice in many demanding engineering applications, but is also very expensive. For applications requiring a polymer with high heat resistance and lower cost, Ultem 9085 would be a great choice. If the application has lower temperature demands and needs a lower cost polymer than PEEK or needs excellent fatigue properties, Nylon 12CF is an established option. While the examined materials are impressive by their own merits, they are not yet a simple replacement to traditional high-end performance materials. As material scientists continue to make advances in polymer science, new and unique materials will be developed to fill additional niche applications. The future of polymer AM is bright and will continue to make great strides in scientific advancements in high-performance applications. Thank you for your time.